Okay, in today's lecture we've looked at X-rays. We started off by considering the historical origin of X-rays and the work that Röntgen did, where he took the output from his cathode ray tube and saw that even after the tube, if he put photographic plate or even phosphorescent strip in the way, a signal could still be observed. He showed that these rays were very penetrating. They even exposed the camera film when it was kept in a closed case. We then saw that Edison took some of these ideas and began the medical implementation of X-rays, although the work that he and Clarence Daly did was upset after Clarence Daly suffered major tumours on the hand following the use of ionising radiation, the first real indication of the dangers of this radiation. We then saw that Lawrence and William Bragg could take the ideas of X-rays and use them when combined with crystals to actually be able to find out important structural information about crystals themselves. And we can see that we can use this kind of crystal diffraction, where because the wavelength of X-rays is so short, we can use it to accurately probe the distance between planes of atoms in crystals. And now we use it to understand the structure of proteins, where the form and shape of the protein is particularly important in working out what its function is. We then went on and looked at X-ray spectra, and we saw that X-ray spectra are made of two key features. The first is a very broad spectrum, which is continuous, which starts at a wavelength lambda 0. Now we can work out lambda 0 by converting all of the kinetic energy of an incoming electron into an X-ray photon with a wavelength HF, which is given by the kinetic energy of the electron. This gives us the shortest possible wavelength for X-rays from this particular sample. The remains of this continuous spectrum comes from Bremsstrahlung radiation, where we consider a reduction in Ke from the electrons as they bend around materials in the target, which is emitted in the form of X-ray photons. We also saw that there was the important characteristic X-ray spectrum. This forms distinct sharp lines which overlie the top of the continuous Bremsstrahlung spectrum. And from these lines we can actually define particular elements. The reason why this is so is because these lines are formed by electron transitions falling into the energy levels closest to the nucleus, so they actually probe the nucleus of the atom very well. And we saw how Moseley took this and came up with his relationship, where he showed that the frequency of these lines, the square root of the frequency, is directly proportional to the atomic number -1. And he showed that this relationship with atomic numbers mirrored identically what was happening in the periodic table, which was arranged according to the chemical properties of materials. And he therefore showed there was some underlying connection between the structure of the atom itself, the nucleus of the atom, and the chemical properties which arise from the electrons. We also saw that we can then use Moseley's relation at the end, if you do the example, to work out things like impurities in X-ray spectra, all of these kinds of things.